Okay, we talked about atoms as the smallest level of organization of matter. So there's all kinds of atoms. Every element on the periodic table, you've probably seen the periodic table, 110 different elements, different atoms. So there's about 110 different atoms that make up all the stuff in this world, all the matter in this world. So what is an atom? Well, let's talk about what it's made of. It's made of subatomic particles. Now, these particles don't really exist on their own. They exist in the structure of an atom. So let's talk about that. Okay, there's three kinds of subatomic particles: protons, neutrons, electrons. Protons, here's the symbols I give for those three subatomic particles. The charge of a proton is +1. The charge of a neutron, there is no charge. It's neutral. That's where we get the word neutron. The charge of an electron is -1 compared to a proton. It's the same charge as a proton, but negative. Okay, electrons hardly have any mass at all. Protons and neutrons are 2,000 times more massive. So electrons are hardly any mass compared to the proton or neutron. So here's the old school picture of an atom up here. Protons and neutrons are jammed together in this very teensy space called the nucleus. The nucleus is composed of protons and neutrons. So overall, the charge of the nucleus is what? Well, you got protons, positive, neutrons, neutral. So overall, the charge would be of the nucleus is positively charged. Because 0 doesn't affect the positive. The electrons are spinning way far away from the nucleus, relatively speaking, and very fast. We can think of them as particles moving very fast, orbiting the nucleus. It's going so fast that last modern scientists think of electrons as a cloud, a location, which is a sphere around the nucleus. So you can see 2 electron clouds here, one right here, and one out here somewhere. You can see the tiny nucleus right in the middle. Okay, so again, almost all the mass of an atom is in its nucleus because electrons weigh so much less than a proton or neutron. There's different names for electron clouds. They can be called electron shells. They can be called orbitals because they're orbiting around the nucleus, or they can be called energy levels. Just to remind you, protons that we said were positively charged. If you have a proton next to a proton, it wants to repel. It wants to really repel, push away. So positive, like charges repel. A negative next to a negative wants to push away from it. It's only when you have of unlike charges do they attract. Unlike or opposite charges will attract. So think about it. The nucleus has all these protons and neutrons usually jammed in this little space. And all those protons, a tremendous amount of energy must be used to glue these protons together because they want to repel. That's called nuclear energy. Okay? And then way out here, the electrons want to get sucked into the nucleus, but they're moving so fast. They're moving so fast that they won't get sucked in. That's a good way to think about it. Because the negatives are attracted by the positives, and there's that tendency to want to fall into the nucleus, just like the moon wants to fall to the earth, but it's going too fast to fall to the earth in its orbit. Okay, if I change this question to most of the mass of an atom is located in, you say, its nucleus. Okay, this is a little confusing, but let's clarify it. An atom, an element, can be used interchangeably. So if you have two atoms and they're different atoms, well, you're talking about two different elements. So an element can only be composed of one type of atom. So if we had hydrogen, it only has hydrogen atoms. So we can have an atom of hydrogen, or you'll find out that hydrogen can chemically bond to form a molecule of hydrogen. So, but in either case, the atom and the molecule are composed of the same type of atom. So these are both considered elements. So that's kind of picky. So if you look on a periodic table, hydrogen is given the symbol H, and there's a number. It's the very first element on the periodic table, and that number is 1. Okay, so hydrogen has 1 proton and 1 electron. So this very out of scale drawing right here shows the Bohr diagram, as they call it, BOHR, of hydrogen. No, I said that there's no neutron. There could be. The neutron number doesn't change the identity of the element. So there's no neutron. Or could have 1 neutron. Or could have 2 neutrons. Or 3 neutrons even. Those forms of hydrogen exist. But we'll talk about that later. So the code, the proton number really is the number that identifies the element type. So hydrogen has 1 proton. Anything with only 1 proton in its nucleus has to be hydrogen. It can have several. It can have 0 or several neutrons, but it will remain with 1 proton. So this is called the proton number, is the code number, is element identity number. If that number changes, If that number changes, so will the element. There won't be hydrogen anymore. So we have a special name for the number of protons of an element. It's called the atomic number. We should know that. And so because hydrogen has one proton, hydrogen's atomic number is 1. If you change that number, no longer is a hydrogen. Again, I'm pointing out the atomic number determines what element the atom is. Change that atomic number, and you'll change the type of element it is. Now, hydrogen could lose an electron and still be hydrogen. So I don't want to say the number of protons always equals the number of electrons, because the electron number can change, and that will not change the nucleus. It will not change the type of element or atom. Okay, so we could have hydrogen with 1 electron. We could have hydrogen with no electrons. So we could have hydrogen like missing electron. You really can't put 2 electrons on it. So this would be hydrogen neutral. This would be hydrogen missing 1 electron. So he's +1. He is missing an electron. He's missing a negative, so he's 1 positive. So the electron number does not have to equal the proton number. The electron number equals the proton number if the atom is neutral, no charge. But if you have more electrons than protons, you'll have a negative charge. If you have less protons than electrons, you'll have a positive charge. Now, before we go on, I have to change something. Okay, these are called nuclear symbols. Nuclear symbols. This is where we just talked about the protons and neutrons in the nucleus. We don't talk about the electrons. This number on top will be, I'm going to switch it around. This is going to be the number of protons plus neutrons. This is called the mass number. And the bottom number will be the number of protons, which is, of course, the atomic number. So if you only had hydrogen with no neutrons, that just means 1 proton. It would be number of protons and neutrons would be 1, because neutrons would be 0. And of course, the number of protons would have to be 1, or else it wouldn't be hydrogen. Then hydrogen with 1 neutron in the nucleus would be H1, because it only has 1 proton. Then the mass number would be 1 plus 1, which is 2. So the mass number is the number of protons and neutrons. So if you had 1 neutron, you'd also have 1 proton, or else it wouldn't be hydrogen. Okay? And then we also have hydrogen with 2 neutrons in the nucleus, and that would be H3, 1. There's 1 proton. Then there's 2 neutrons plus 1 proton makes 3. Okay, so this kind of way of showing the atomic number on the bottom and the mass number on top is going to be useful in chemistry, and well, not too much in biology, but anyway. So these 3 examples show 3 isotopes. That's a new word. Of hydrogen. An isotope is defined as atoms of the same element with different number of neutrons. Now, that's not to be confused with ions. Ions are atoms of the same element with different number of electrons. Where atoms of the same element with different number of protons. Where atoms of the same element with different number of protons. That doesn't make sense. If atoms have different protons, they aren't the same element. If you look at a periodic table, helium is the 2nd element. So helium would be, it has 2 protons. The most common isotope of helium has 2 neutrons. So the mass number will be 4. So the top number would be the protons and neutrons. The bottom number would be protons, like you just said. If I want to determine the neutrons from this picture, all I do is take the proton number and subtract it from the mass number. So the neutron number equals mass number minus the atomic number. So it's set up like a sum, so you can just subtract them to find the neutron number. So here's an example of an isotope of helium. And if I just gave you this box right here, you should tell me, okay, how many protons does it have? Well, look at the bottom number. It's 2. How many neutrons? Remember, you got to subtract these to get, you got to subtract the bottom number from the top number in order to get the number of neutrons. So 3 minus 2 is 1 neutron. Once again, the bottom number can never change, or else it wouldn't be helium. The top number can change because the neutron number can be different. And so can the electron number. But you change that bottom number, the atomic number, and you don't have helium anymore. Okay, when I give you a problem like this, I'll give you the nuclear symbol like that in a box. The atomic number of hydrogen is, well, it's the bottom number. So it's 1. That's the number of protons. Okay, once again, I would give you this. The atomic number of helium is 2, because that's the number of its protons. Okay, once again, I'd give you hydrogen like that. Most of the mass is due to, well, there aren't any neutrons in this hydrogen atom. So most hydrogen atoms don't have that neutron. So it's only protons. Okay, subtract those numbers. 1 minus 1 is 0 neutrons. Subtract these numbers and you'll see that the mass is the protons. Now if it was H21, the isotope of hydrogen shown above, then it would be A and B, protons and neutrons. Okay, helium, I'd give you it, the box with the nuclear symbol in it. So helium would have two neutrons, 2 protons. So most of the mass is due to the nucleus, which is both protons and neutrons. Chemistry is the study of chemical reactions or changes. When a chemical reaction occurs, no new elements are made. You don't end up with different elements from what you started out with. The elements just rearrange themselves and form new combinations together, bonded. Okay, we're going to talk about chemistry a little bit, and this will prepare you for your chemistry class next year as well. Now, when elements or atoms chemically react with each other, it's not the nucleus that's having anything to do with that. The nucleus is locked up in the very center of an atom, and it really is not approachable by another element's atom. So it's only the outer shell electrons that take part in chemical reactions. Either the electrons are transferred, that means given, taken, released by one atom and taken by another atom, or they're shared. The outer shell electrons might be shared between the two atoms that are chemically reacting. So it's the electrons that are the actors in the chemical reaction play. When atoms react, they follow a basic rule. First of all, the reason they react is to become more stable. Stable means non-reactive. So an element that is not stable chemically is looking for another element to react with so that it can become more stable. Now, what makes you unstable is if your outer shell, electron shell, is unfilled. So if the outermost electron shell that an atom has electrons in already is not filled up, that atom is unstable. So let's talk about simply hydrogen. Hydrogen just has one shell right? One proton or maybe a neutron or two. And the first electron shell will be filled when it has two in it. Okay? So the first electron shell is unstable if there's only one electron in it because two will fill it. Okay, how many electrons does a neutral hydrogen M have? Well, it's the same number of protons. And hydrogen has one proton because this is the first element in the periodic table. I would give you this symbol for hydrogens. And you would just say, okay, that means the bottom number is 1, so that has one proton. If it's neutral, the proton number equals the electron number if it's neutral. So the hydrogen atom has one electron in its outermost shell. Will an isolated hydrogen atom be stable? So I'm going to say isolated. He hasn't reacted yet. I don't really like that way they use that word. So I'm going to say, well, unreacted hydrogen atom be stable? No, because it wants another electron in its outermost shell in order to be stable. So no. How many electrons does a helium atom have? Okay, I would give you the nuclear symbol. Okay, so how many protons does it have? 2. So how many electrons, if it's neutral, does a helium atom have? 2. Look at the bottom number. Now, what if I asked you, is helium stable? It has 2 electrons in its outermost shell, which is the first shell. Yeah, it's stable. It has 2. It's filled up to the max. I think that's the next question. Will an unreacted helium atom be stable? Yes. Its shell is filled. Its outermost shell is filled, as I described on the previous page. Okay, helium is therefore unreactive because it has a filled outer shell. It's stable. It's chemically stable. Helium does not need to react because with another element because it's already possessing a filled outer shell. We call the family that helium is in the inert gases, which means unreactive. So here we go again. Hydrogen is 1,1. The hydrogen atom has 1 electron in its outermost shell. What would be a solution to the problem to make it stable? Because right now it's not chemically stable. So how does it become chemically stable? Well, it picks up an electron. And once it does that, it doesn't change the nucleus. It's still hydrogen with a 1 proton. It becomes stable because its outer shell is filled. Again, elements will react until their outer shell is filled, and then they become stable. So what they're showing here is you got 2 hydrogen atoms, each one having 1 in its outermost shell. And what they do is they just share that electron so that they both get a filled outer shell. This is called a covalent bond. And we represent it by a stick. The 2 shared electrons represent by a stick between the two hydrogens. Okay, this is called the structural formula. When you show the toothpick bond, covalent bond is actually called, but we'll talk about that pretty soon. When the electrons are shared, one stick represents two shared electrons, a shared electron pair. Okay? This is called, right here, this is called the Lewis dot diagram, or just plain Lewis diagram. Okay, so when electrons are shared to form a chemical bond, this is called a covalent bond, as they said right here. And this is kind of important. Atoms held together by covalent bonds are molecules. So right here is a hydrogen gas molecule made of two hydrogen atoms. It's also an element, hydrogen, because only one type of atom is in the molecule. So let's say some more things about covalent bonds and molecules. Okay, this is just indicating you when you have a subscript, that means that means there's two of what came before that subscript. So in this case, two hydrogen molecules chemically bonded together, but one molecule. They don't write the one in front. That's called a coefficient, because it's assumed if there's no other number there. So that's the coefficient. That's the number of molecules, and that is a subscript showing you how many atoms are in the molecule. Now, different elements need to borrow different number of electrons, as you'll find out. Hydrogen only needs one electron to fill its outer shell, so it can only form one bond with another element, like another atom, like hydrogen. So once again, we got one hydrogen plus another hydrogen will get together and form a stable element of hydrogen. Okay, because each one now has two electrons. Each one now has a filled outer shell. Remember, the first electron shell, the one closest to the nucleus, is filled when you put two electrons in it. So these guys are reactive. The reactants, as we say, the elements on the left side of the yield arrow, are reactive. And hydrogen gas is unreactive comparatively, because now both of the atoms have a filled outer shell, making them stable. Okay, so they're repeating what I just said before. Another rule of chemical reactions is that what you start out with, the number of atoms of each element that you start out with, you have to end up with. You can't just have atoms disappear or come out of nowhere. It's called a conservation of matter. Conservation means saving. What you start out with, you have to end up with. No more, no less. So if we look on the left side of the reaction, we only have one element, so it's easy. We got two hydrogens, two unreacted hydrogens. If you look on the right side of the reaction, we have one hydrogen molecule, but 1 times 2 would mean 2 hydrogen atoms, or 1 hydrogen molecule. But the point is, these have to be balanced. That's the law of conservation of matter. So just to emphasize, the law of conservation of matter is the second rule we want to follow when we're talking about chemical reactions. Conservation of mass is basically the same thing as the conservation of matter, because we had the same number of each type of atom before reaction as we do at the end of the reaction. There's no change in the mass of the products after the reaction compared to the mass of the reactants before a reaction. Okay, so let me just emphasize that the reactants are the chemicals before a chemical reaction, and products are the chemicals after the chemical reaction occurs. And so you can't lose or gain mass, which is like weight, because you're not losing any balls, different balls, if you think of the balls as atoms of different elements. But to be transparent with you, conservation mass and conservation matter are basically the same thing. Okay, so here's the structural formula of H2. Okay, this is the chemical formula right there of hydrogen gas. This is right here with drawing a stick between them, a single covalent bond. That's the structural formula with the stick. Okay, this right here with the shared bonds, the electrons in the covalent bond, that is Lewis dot structure. We show the electrons in the outermost shell. Okay, one hydrogen molecule is comprised of how many atoms? Well, one hydrogen molecule is H2. That's 2 atoms of hydrogen. Okay, molecules are held together by covalent bonds. Chemical bonds that result in sharing electrons are called covalent bonds. When electrons are shared, they form what is called a covalent bond. According to conservation of matter, the number and type of any type of atom before and after the chemical reaction has to be the same, has to be unchanged. You don't end up with more or less of what you started out with. This is kind of an ambiguous question. What particles, what do they mean? Well, I mean atoms or subatomic particles like electrons, protons, and neutrons. All that's matter. All that has to be conserved, not changed before and after a reaction. Okay, once again, conservation of mass. If the amount of matter is not changing, the mass of the matter is not changing either. Mass being like weight. Conservation means unchanged, saving. Okay, now we're moving beyond hydrogen. Bigger elements with other shells being their outer shell besides the first electron shell. So let's investigate some of these. Again, same rule applies. An atom will be chemically reactive or unstable until it fills its outermost shell, at which point it becomes stable and unreactive. Okay, if we look at the periodic table here, which is a list of all 102, it looks like, elements that exist. Really, there's like 110, 115. But those are synthetic elements. But anyway, the up and down rows. The columns, up and down columns, vertical columns, are called groups or families, also called families. In the horizontal groups of elements, like right here, they are called periods. So these are the period numbers here. So period 1, period 2, period 3, whereas these are the families. Family 1. Right here, these numbers. Family 1, family 2, and all these guys in the middle. Family 13, 14, 15, 16, 17, 18. Now you can skip the ones in the middle. Call this family 3, 4, 5, 6, 7, 8. That's a better way to do it. Okay, how many periods are there on the periodic table? 7. Now the periods represent the number of electron shells. Around the nucleus. One more thing to say, which is important. These are the most important elements in living things. Hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. Okay, the inert gases, noble gases also called, are in family 8, or family 18 if you want to count all the guys in the middle as different families. But I like to do family 8. Now, all the gases in family 8 are unreactive because they have filled outer shells. So having a filled outer shell makes them stable or inert, unreactive. They're not going to want to react with anybody, any other element. And so you don't see them reacting in chemical reactions. Any elements that consist of 2 of the same atom combined together covalently, for example, hydrogen gas is a diatomic molecule. Now, diatomic molecules have to have the same atom type, and only 2 of them. So That's what that term means. There's always a subscript 2 next to one element to make that molecule. Now, these are other diatomic gases: nitrogen gas, oxygen gas, and fluorine gas. Now, before we get into this, it's very important that you understand that only the first electron shell is stable with 2 filling it. Every other electron shell, 2, 3, 4, 5, 6, or 7, will be filled as an outer shell with 8. So 8 electrons need to be filled for any other shell past the first shell, if that's the outermost shell. So the second electron cloud needs 8 electrons in it to be stable. And so, same with shell 3, 4, 5, 6, 7, and that's all there are. If those are the outer shells, they will be filled with 8 electrons, making the element chemically stable. So here we see neon. Neon has, let's see, 10 protons. If you look at the periodic table, you can find it under helium. And you can see that its atomic number is 10, so it has 10 protons. And so neon, if neutral, has 10 electrons. So if you look at neon on the periodic table, it's in period 2. So it has 2 rings, or 2 electron shells. Okay, so neon would be 1 shell, then another shell. The first shell will be filled with only 2. Then the next shell is kind of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I kind of make them in that kind of pattern because electrons repel each other. They want to be as far away from each other as possible because they're all negative. But anyway, so we got 2 in the first shell, and in the second electron shell, which is now the outermost shell, we got 8. So neon has a filled outer shell, and it's completely unstable, meaning it's not going to chemically react with anything. Now let's look at oxygen. So oxygen has 6 protons, so neutral oxygen has 6 electrons. So it's in period 2. If you look at a periodic table, it's in period 2. It's a horizontal group of elements, number 2 from the top. So it has 2 rings. And so let's count them. 1, 2, and then 1, 2, 3, 4, 5, 6. Is oxygen stable? No, it's not stable because it does not have a filled outer shell. It needs how many more electrons to be stable? Well, how many electrons you need in the outer shell to be stable? Well, if it's the first outer shell, you just need 2. But in the second, third, fourth, fifth, sixth, seventh outer shell, you need 8. So 1, 2, 3, 4. 6 doesn't cut it. It needs 2 more electrons to become stable, because that will fill its outer shell. So that's how it will react. It will react by looking for 2 more electrons. The chemical formula for water is H2O. That means 2 hydrogen atoms and 1 oxygen atom. They don't put the subscript 1 because it's assumed if they don't put a number there, it's 1. Okay, so let's see how this is happening. So we got 2 hydrogen atoms, each one with 1 electron. Now I'm going to do a Lewis dot diagram. Just show the outer shell. And then the outer shell of oxygen has 6, so I do it like this: 1, 2, 3, 4. Then I pair them 5, 6. I kind of make this an X instead of a dot, or you can do different colors. Now you can see that oxygen wants 2 more electrons, so 1 there and 1 here. Okay, to give it 8. So what's going to happen? 1 hydrogen is not going to satisfy 1 oxygen to make it stable. So what's going to happen is, here's oxygen with its 1, 2, 3, 4, 5, 6 electrons. Here's the hydrogen is going to come over here and share electrons with that oxygen. And then another hydrogen will come around and share electrons with that oxygen. So, I mean, I can put these little Venn diagram things in to show you who's sharing what. Okay, so that's the Lewis dot diagram, but here's the stick formula, or the structural formula of hydrogen. Okay, so oxygen has attained 2 electrons by sharing with 2 hydrogen atoms, and each hydrogen atom is happy or stable with a filled outer shell. Remember, hydrogen only needs 2 in its outer shell. Oxygen needs 8. Okay, so here's some kind of review questions. Any element is defined by a number of, what's their code number, their atomic number, the number of protons. Atoms within diatomic molecules share electrons because they want, they want they want to attain the same number of elements of electrons as an inert gas. That just means a filled outer shell. They want to get a filled outer shell, electron shell. So that's letter C. Inert elements are stable, chemically stable. True. They don't want to react. They already have a filled outer shell. Why bother changing a good thing? All molecules include at least 1. Okay, molecules we're talking about. Covalent bond. That's the shared electrons between the atoms in the molecule. Okay, carbon is probably the most important element to living things. We'll kind of explain why. Okay, carbon is, if you look at the periodic table, 12,6C. Okay, I'm putting it 12 and 6 in front. Some books do that. Some books do it on the right. So you should be flexible. So how many protons does carbon have? I mean, you could look at it on a periodic table, or you can look at this nuclear symbol. Okay, it has 6 protons, atomic number. So neutral carbon, unreacted carbon, has 6 electrons because the number of electrons equals the number of protons. So here we got the 2 shell. Carbon is in the second row across. So carbon has 2 energy shells. Okay, let's count them. 1, count the electrons. 1, 2, and then you have to go to the next shell because the first shell only holds 2. 1, 2, 3, 4, 5, 6. So carbon has how many more electrons it needs before it's stable? Well, it has 4 in our shell. What makes our shell full and makes the atom stable? 8 if you're not the first, if the first shell is an outer shell. So carbon can get 4 more places that to form bonds. It has openings for 4 more electrons. Until it gets 4 more electrons, it remains unstable. So carbon needs to borrow 4 more electrons, share them, become stable with a filled outer shell, like if you go across the periodic table like neon in the same period. So carbon can make up to 4 covalent bonds with other elements. So carbon is very important because you can hook more things up to carbon than any other elements. If it was hydrogen, you can only hook one thing to hydrogen. If it was oxygen, you can hook 2 things, but carbon, you can hook 4 different atoms covalently to it. And that gives a lot of variety for a lot of choices for different molecules that a living thing needs. So carbon is basically the backbone of large biomolecules because you can hang so many different things on it. And carbon will, of course, combine to itself as well, making long chains or rings. Okay, so in this picture right here, we see carbon needing 4 more spaces. If hydrogen's around, hydrogen needs 1 electron, carbon needs 4, so carbon's going to react with 4 hydrogen atoms to form methane gas, CH4. So you can see that we've hooked 4 hydrogens up to 1 carbon. All the hydrogens are now stable, unreactive, with 2 electrons in the shared bond with carbon, and the carbon is stable with 8 electrons in its outer shell, and therefore unreactive. So carbon is the basis of all life on Earth because of its versatility in the kind of molecules, different kinds of molecules that it can build. The study of carbon molecules is called organic chemistry. Okay, here we have an example of glucose, or simple sugar. C6H12O6 is the chemical formula. And right here, with the balls and sticks connecting them, we can see that That's the structural formula. Now notice how carbon, designated by the black balls here, makes up the backbone of glucose molecule. Everything else is hooked onto that. The red ones are oxygen atoms, okay? And the gray ones are hydrogen atoms. Okay, so you can see each hydrogen has one stick. Each oxygen has two sticks. And each carbon has four sticks. 1, 2, 3, 4. And so you can build these gigantic molecules. Glucose is not a gigantic molecule, but you can get the idea that the carbons can just keep on being hooked up till you have a huge molecule. So glucose is a very important molecule. It's made in photosynthesis. Plants produce it. And I'll talk more about that later. This is a periodic table showing the difference between metals and nonmetals. Okay, we also have metalloids, but they can act like metals or nonmetals depending on what they're reacting with. So, just generally speaking, these guys are the nonmetals, groups 4, or family 4, 5, 6, 7, 8. And then hydrogen up here acts like a nonmetal. Now it's the nonmetal atoms, when they react with other nonmetal atoms, they share electrons. Therefore, they form covalent bonds. When metals, the yellow ones in here, act with the green ones, a nonmetal, then we have an ionic bond forming. Okay, so we already know what a covalent bond is. So the covalent bonds are sharing electrons between nonmetal and nonmetal atoms. Okay, we just talked about those. Now we're going to start talking about ionic bonds. Ionic bonds are when a metal and a nonmetal react with each other, chemically react with each other, by actually transferring electrons, not sharing electrons. One guy loses and one guy gains electrons. There's no sharing. Of electrons. They're transferred. For ionic bonds, again, ionic bonds are between metal and nonmetals, whereas covalent bonds are between nonmetals and nonmetals. Up here at the periodic table, it's in family 2, and fluorine is in family 7. Okay, sorry, I jammed a whole bunch of slides on this page, so you have to scroll down with me. So, when an ionic bond forms, a metal atom gives away its electron to a nonmetal atom, which takes the electron. So the metal gives, the nonmetal takes. And this results in a stable electron configuration. What they mean by that is both the metal and the nonmetal atoms achieve a filled outer shell, electron shell. Scroll down. So let's explain how sodium chloride, NaCl, forms. First of all, we know that, you probably know that's the chemical formula for sodium chloride, table salt. Now, when you think of salt, you think of table salt, but all ionic compounds are called salts, not molecules. They don't form molecules, they form salts. So, these words go with these pictures down here. So I look up sodium on the periodic table, and sodium has an atomic number of 11. So the proton number equals 11. So before it reacts, the number of electrons also equals 11, because the number of protons is equal to the number of electrons for the neutral atom that hasn't reacted yet. So what period is sodium in? It's in the third period, so there's 3 shells. So sodium, look at the picture so I don't have to draw it. There's the first shell, the second shell, and third shell in sodium. Now that's what they mean by this 281. So 2 plus 8 plus 1 is 11. So that's 11 electrons. And they're spread out with 2 in the first shell, 8 in the second shell. And that leaves a 1 in the outer shell. Now, you do the same thing with chlorine. Chlorine is number 2817. Okay, so the proton number is 17. So the electron number is 17 as well. So how are those electrons spread out? First shell, well, again, chlorine is in the third period, so it has 3 shells. So having 3 shells, so the first electron shell has 2, the second one has 8 is filled, and then the third one has 7. Okay, now think about it. Chlorine's a non-metal, and sodium's a metal. Sodium wants to get rid of that electron in the outer shell because it's so much easier to get rid of one and then call your second shell, which is already filled, your outer shell. So you just shed that electron in the outermost shell, and then your outermost shell becomes the second shell with 8. And then chlorine can just take that electron and put it right here. Okay, so that's what they're doing in the next picture. You can see that happening now. You don't see any football with shared electrons. Okay, you got 2 separate ions. When the sodium has lost 1 electron, so he's become a positive ion, as shown by that. And chlorine has gained 1 electron and has become a negative ion, therefore. Okay, so that's basically all you do. Now there's a shortcut to do this. So sodium plus chlorine forms what kind of salt? Okay, so I look at sodium on the periodic table. He's in family 1, group 1. Okay, think about it. If you're in group 1, you got 1 electron in your outermost shell. Is it easier for sodium to gain 7 to make 8 electrons in its outer shell, or to lose 1 and then keep its underlying shell as the full outer shell? Well, obviously, it's easier to lose 1. If you lose 1 electron, you become a +1 charge. Okay, and then chlorine. Chlorine is in period 7. I'm sorry, family 7, group 7. So he has 7 valent outer shell electrons. He only needs 1 more, so it's easier just to get 1 more electron. When you gain 1 electron, you become a -1 charge. I call this a cross arrow method. To determine the subscripts, you just bring these over like this. And so my answer is NaCl. 1, 1, but I don't write the 1s down there. Okay, so let's do a fancier one. Magnesium fluoride. So magnesium plus fluorine goes to form what kind of salt? Okay, magnesium's a metal. If you look, so magnesium in family 2 has 2 outer shell electrons. Is it easier to gain 6 to make 8 or to lose the 2? It's easier for magnesium to lose the 2 electrons. So he becomes +2. Fluorine is in group 7. That means it has 7 valence electrons. Is it easier to lose the 7 to use this outer shell underneath as a full outer shell, or is it easier if you have 7 electrons to gain 1? So much easier to gain 1. So fluorine has a 1- charge. So you just flip these around, the numbers. Magnesium has a 1 subscript and fluorine has a 2 subscript. So this would be magnesium 2 plus fluorine minus with a 2 subscript on fluorine. Magnesium fluoride. Okay, and that's what this picture is showing. I think it's easier to use a shortcut. Okay, so magnesium has 2. It needs 6 more, or it could lose the 2 and then use the underlying shell as a full shell. Then fluorine just needs 1. So magnesium has 2 to give, 1 to give him, and 1 to give him. Not to share, but to give it away. This is an ionic form, ionic bond between the 2. You can see that's what happens here. Now, let's figure out what kind of salt formula forms from these. So lithium plus fluoride forms what kind of salt? Okay. Once again, if you look at the periodic table, lithium is in family 1, so he has 1 electron in his outer shell, so it's easy to lose that and call the underlying shell the outer shell, which would then be filled. So if you have 1 electron in your outer shell, you're a metal, you're going to lose that guy and become +1. Fluorine is in group 7 with 7 outer shell electrons. It's easier to gain 1 electron. So he'll become a native one when he gains that electron. Okay, you cross multiply the 1s. You just bring the 1s down and you'll get, which is just lithium fluoride. Sodium oxide. Sodium is in family 1. Oxygen is in family 6. So, family 6, you got 6 electrons in your outer shell. You need 2 more to get 8. So, when you gain those 2, you'll become 2 minus, and cross arrow the charges to get the subscript, and so we'll get Na2O with Na having a +1 charge and oxygen having a 2 minus charge. So there'll be 2 sodium ions for every 1 oxygen ion. Okay, magnesium oxide. Magnesium plus oxygen. I really should go over here and put a 2 here because 2 oxygens combined with 1 Na. Okay, so back to magnesium oxide. Magnesium is in the 2nd family. So he has 2 valence electrons. Hey, but valence electrons are the outer shell electrons. So if I say that, that's what I'm talking about. So magnesium has 2 outer shell electrons, 2 valence electrons. Oxygen, I already said, has 2 minus. So what we do, cross these over to find the subscripts, and we get Mg2O2. But that simplifies to MgO, 2 plus, 2 minus. Okay, boron oxide. Boron plus O. Okay, boron is in group 13, which means it has 3 valence electrons. Okay, it's a metal, so it's easier to lose those 3 valence electrons rather than gaining 5 to make 8. So he'll lose those 3 valence electrons. Oxygen, we already did, is in group 6. He needs 2 more. So cross multiply. We get B2O3. Okay, I should put so 3 oxygen ions and 2 boron ions. Okay, finally, aluminum oxide. It's the same thing because aluminum's in group 3 with boron. So we got aluminum plus oxygen to form aluminum something, oxygen something. So aluminum's in group 3 with boron, if you look at the periodic table. Oxygen's in group 6, needing 2 more electrons. And so I cross multiply those things. So aluminum will be 2 and oxygen will be 3 subscript. And the charges stay low. Then I would just go back and say, okay, there's 3, just to balance the equation, which you're not going to even have to worry about. You probably just have to figure out what the subscripts are. We don't have to draw these pictures to explain what I just showed by the shortcut, but it's good to know what's really happening when an ionic bond forms. So you should be able to, if I give you a metal and a non-metal, tell me which one gains electrons, which one loses electrons, how many electrons are involved, what would you predict the chemical formula to be. Salts form crystals, salt crystals. I mean, you've seen them when you shake salt on something. You can see little crystals of salt. Those crystals contain billions of atoms linked together by ionic bonds. So this picture right here shows a piece of a salt crystal. Maybe it's sodium chloride. You can see that you got repeated in all dimensions molecule of salt. Now, we don't call it a molecule like a water molecule. Water molecules don't exist linked to other water molecules by bonds. But in a salt crystal, the formula unit is what we call it, not a molecule, because it's a molecular. It's ionic, not covalent. So it's not equal to a molecule. But it's like a molecule, but it's repeated over and over to form the salt crystal. No matter how big the salt crystal is, if the formula is NaCl, you always have the same amount, the same ratio of sodium to chloride, 1:1. For every green ball there's a purple ball. The green ball represents chlorine. The purple ball represents sodium. If it was Al2O3, that salt, the ratio of aluminum to oxygen would be 2:3. So you'd have 2 aluminum balls for every 3 oxygen balls in the salt crystal of aluminum oxide. But the crystal can be as big or as small as you want it to, as it can be. For molecular substance, you still have a fixed ratio. The hydrogen-oxygen ratio is 2:1, but 2 hydrogens for 1 oxygen. But the water molecules don't form a crystal unless it's ice, solid. That's not ionic bonds holding it there. We'll talk about those kind of bonds later. Okay, so these are simple, more like the questions I can ask on your test rather than asking you to draw pictures or anything like that. An ionic bond is formed by the what of an electron between 2 atoms. Well, it's not sharing. That would be a covalent bond. So it's the taking and giving or the transferring of electrons. A covalent bond is formed by the sharing of electrons, which are formed by covalent bonds. All of them, they're all nonmetals. When sodium combines with chlorine, sodium is a metal, chlorine is a nonmetal. You could look at a periodic table and figure that out. But in ionic compounds, the metal always goes first, followed by the nonmetal, like sodium chloride. The first one's the metal, the second one's the nonmetal. So we're talking about ionic bond. Metals lose electrons, and nonmetal gains electrons always. So there's that one. Ionic bonds are formed between, think about a metal and a nonmetal. Yeah, elements on opposite sides of the periodic table, right? Here's the periodic table, kind of. The metals are on this side, like, and the non-metals are on the right side. Bonds formed by a specific number of atoms sharing electrons with sharing electrons. Okay, just knowing that sharing electrons is covalent bonds. Bonds formed by one type taking electrons from another, blah, 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 to form an extended structure, which is called a crystal or ionic. Molecules are covalent compounds. So covalent bonds form molecules. Okay, so we're done with bonding. Now we're just talking a little bit about some extra things that will pop up in biology once in a while. A solution. Okay, think of soda pop, some like Dr. Pepper or something. Okay, you got water, you got the fizz, carbon dioxide, you got flavorings, you got sugar, and it's all mixed, and you can't see the different pieces. It's homogeneous. You can't see the different components. It's all mixed in one thing. You can't see them with a microscope. Okay, so a solution consists of a solute and a solvent. Solvent is a substance that dissolves the solute. Solute is the stuff being dissolved. So like iced tea, water is a solvent, or in Dr. Pepper, the water is a solvent. It's what you have more of. It dissolves other stuff. And the flavorings and the carbon dioxide and the sugar would be the solute, and together, when mixed, it forms a solution. So solvent is the thing that you have the most of. So in Dr. Pepper, the main component is water. And solute is a little bit of this, a little bit of that, that's dissolved in the water, in the solvent. So the bigger word is what you have more of, more letters. That's the way to remember it. Okay, we will be talking about liquid solutions, but gas can be dissolving, so either one of these. The air is a combination that we breathe is a solution of different gases, but basically in biology we'll be talking about liquid solutions where the solvent is the water, the liquid, basically water. Yeah, for us, it'll always be water for living things. And a gaseous solution like the air we breathe, the major component of the gas solution is a solvent. In the case of air, it would be nitrogen. Most of the air we breathe is nitrogen. Only a little bit is oxygen. Nitrogen doesn't do anything for us, by the way. So gaseous solutions, we might talk about that too. Okay, the concentration of a solution. The concentration of a solution is like the amount of solute dissolved per solvent. Okay, so there's a lot of solute dissolved. Then the solution is considered concentrated. You can think of if you added sugar to your coffee, let's say, and you add a whole bunch of sugar, the water in the coffee dissolves that sugar, but it's really super sweet. And that would be a concentrated solution. If you just added a little bit of sugar, that would be a dilute solution or a low concentration. Okay, so if it's concentrated, it has a high concentration of solute dissolved. Okay, an acid is a type of solution that has a lot of hydrogen plus ions. Hydrogen that has lost its one electron. The more H plus ions dissolved in water, the more acidic something is. A base is a solution that has an excess of this kind of ion, hydroxide ion, OH minus. Hydroxide ion. Bases have more OH minus dissolved in them than H plus. Okay, if you have a neutral solution, it has equal numbers of H plus and OH minus ions. They kind of neutralize each other and form water. Okay, you should get familiar with the pH scale. pH scale is a scale going from 0 to 14. 0 is the most acidic, and 14 is the most basic or alkaline. The name for basic is alkaline. Neutral, like pure water, distilled water, has a pH of 7. So distilled water has a pH of 7, right in the middle, where the OH and the H plus equal ion concentration equal each other. So as you go up on this, as you get closer to 0, you get much more H plus than OH minus. And as you get closer to 14, a pH of 14, you get much more hydroxide ion than hydrogen ion dissolved in the water solution. So you should know that. So H plus increases as you go down to 0. Concentration of hydrogen ions and the concentration of hydroxide. This means concentration when you put brackets. The concentration of hydroxide solutions is greater as you get closer to 14. And you should know that a pH of 7 is neutral. Right here.